Now let's talk about the MapReduce distributed aggregation algorithm. So this is a way for us to compute across very large files. You may have seen it in the 61A book, CS61A book, or if you took CS61C. So in this class, the way we've been interacting with data is we request a sample of data from our big data lake filled with ones and zeros, and we compute locally. So we apply some function or some algorithm, and we tune our algorithm on that data. And we might request a different sample of data so we can do some validation, cross-validation or evaluation of our algorithm. And there are lots of tools that allow us to work with these smaller data sets that fit on a single machine. But now, today, we've looked at data sets that don't fit on a single machine. And so what could we do instead? Well, we saw how we could store those data sets in clusters or in the cloud. And so now we can think about, instead of trying to move the data to us locally to do our computation, we move our computation to the cloud where we have lots of compute resources, or to a cluster. And so here, our query is a function that we want to evaluate across a portion or maybe all of our cloud data set. And then we get back the result as our response. And then we tune our algorithm and again pass a different function to the cloud or our cluster for compute. So how does this work? Well, let's start with a simple example. How would you compute the number of occurrences of each word in all of the books using a team of people? So we've got a library here. We want to take a team of people and have them count each word. How many times does it appear in all of these books? Well, a simple solution would be to take our team and we divide the books across individuals. So the individual on the top gets the first two books, the individual on the bottom gets the second two set of books. And so each one of them is going to count the words in the book, generate a table of counts, and do that locally. The next step is to take and aggregate those tables. So here we can see that in the first set of books, Apple appeared twice, and in the second set of books, Apple didn't appear. But bird appeared once. In the first set, it appeared 7 times. So in our aggregation, we have Apple appearing twice in our set of 4 books, and bird appearing 8 times in our set of 4 books. And so it's this approach that led to the MapReduce abstraction done by Jeff Dean and Sanjay Ghemawat at Google, and published in an OSDI paper in 2004. And I encourage you to read that paper to learn more about how MapReduce works, because there are lots of trade-offs that you have to do to actually make this algorithm work in practice. But here's the basic abstraction. We have records. For each record, we apply a map function. That map function is going to generate a set of keys and associated values for each key. This could be word count, and the key would be a word, and the value would be the number of times that word appears in the record. And so our map function is given a book. For each of the words in the set of words in that book, omit that word and the count of the number of times that word occurs in the book. Okay, so that's going to generate a bunch of key values where, again, each key is a word that appears in the book, and the value is the number of times that word appears in the book. So now we're going to end up with a set of keys where for each key, there's going to be a number of values. So as an example, bird appeared 7 times in one book and once in another book. So we need to take all of those values for a given key, and we want to reduce that down to just the word, and in this case, the sum of those values. And that's our reduce function. So our reduce function takes a key, a set of keys, same key, and different values, and reduces it down to just that key and a single value. So in this case, we'll take for a given word and a set of counts for that word. We'll sum all the counts up and omit the word and the sum of those counts. Okay, so a simpler version of this is that rather than doing that sum locally as part of the map, every time we see a word, we just omit that word. So we're just going to say, I saw a word and a 1. And then our reduce is the same. It's just going to take, for all of those word and one pairs, it's going to sum them together and just emit word and the sum of all those individual ones. So there's some important properties that we have here. Our map has to be deterministic, and our reduce function has to be both commutative and associative, right? And so both of these have to have those properties hold true, or MapReduce isn't going to work. Okay, so let's dig down into that a little bit more. Okay, so it has to be deterministic for our map, which means that we can re-execute a map if there's failure. Given a set of input, we will always get the same output when we apply the map function. So if a computation fails or is lost for some reason, we can always just recompute. But what if we have samples? Well, a solution is to use random seeds and to record the random seed. If we record the random seed, then we can just sample again and run that again with the same sample chosen randomly because the seed is recorded, and we'll get the same result. It has to be commutative for our reduce so that we can reorder the operation. So that means if we have reduce A, B, it's going to be equivalent to applying reduce to B and then A. So addition is an example of a commutative function. A plus B equals B plus A. It also has to be associative for our reduce. And this allows us to regroup the operations and do them in any order that we choose. So we could do reduce of the reduce of A and B followed by C, and that'll be equivalent to the reduce of A followed by the reduce of B and C. All right, so we can do them in any order. Example here is max, right? The max of A and B, and then the max of that with C, is equivalent to saying we're going to take the max of B and C first, and then take the max of that along with A. Now, one thing to be cautious about is when you're doing floating point operations, depending on what kind of floating point operations you're doing, they're not guaranteed to be associative. So addition is not always guaranteed. Depends on the implementation of floating point and the resolution that you're using. So here's a question. Suppose that our reduction function computes the following: A times B plus 1. Now, let's say we have the key cat, and it has three values, 3, 2, and 1. What's going to be the result of this reduction operation? Think about it for a moment. Try writing it out. Okay, well, the answer, it depends. It's going to depend on the order, right? If we do 3 times, the first two, 3 times 2 plus 1 is 7, and then 7 times 1 plus 1 is going to be 8. But we get a different result if we do 1 and 2 first. And we get a different result if we do 3 and 1 first. So this is not an associative function, and so this is not a good reduce function. This won't work. Okay, so let's look at how we execute MapReduce. So we have our record. The map takes and generates a set of keys and values from that record. And so we distribute that map function across all of our machines. So we're running all of those map functions in parallel. So we can take and apply the map function to B on machine 1, to C on machine 2, to A on machine 3, and D on machine 4. All right? So they're all running in parallel. And the output, we cache that. And that lets us have fast recovery if a node fails. All right. So the reduce function, we can run that on many machines also. And so here we're running the reduce function in parallel. So we take all the key value pairs associated with the key apple and reduce that. We take all of the key value pairs associated with the and reduce that. Same with cat, same with big, same with dog. All of these run in parallel. And so we're going to get the output, apple 1, the 3, cat 5, and so on. Now, what happens if one of our reducers fails? Say the reducer that was working on cat. Well, we can simply recreate it because we save the outputs of the map and just run it on a different machine. So maybe we run it instead on, if that was machine 2 that failed, maybe we run it on machine 3 instead. And so this is the advantage of MapReduce. It can run on commodity hardware. If something fails, we've saved copies of the map outputs, and we can just simply rerun the reduce operation.